In this video, I'm going to talk about ocean acidification, one of the most important environmental issues facing us at the moment, and yet one that seems to get very little attention. So I suspect that we're all aware that our society has been burning fossil fuels at a significant rate for many decades now, really for many centuries. And we have therefore been producing large amounts of carbon dioxide that get emitted into our atmosphere. And it has certainly been noted that there are problems associated with doing that. There are great concerns about the potential for climate change as a result of the fact that carbon dioxide is a greenhouse gas. But that's not the only consequence of significantly increasing the carbon dioxide levels in our atmosphere. As you'll see in Chem 2000, there's a mathematical relationship described by Henry's law that states that the amount of a substance that dissolves in water is directly proportional to the amount of that substance in the atmosphere above it. Henry's law, therefore, obviously used to describe solubility of gases. So what that means is that if we have increased the atmospheric carbon dioxide levels by, say, 35% since pre-industrial times, which we have, then that means that we have also increased the amount of carbon dioxide dissolved in our lakes and oceans by 35% over that same time frame. Now, carbon dioxide, as we've been seeing, is a Lewis acid. When carbon dioxide exists in an aqueous environment, it can react with the water, and our water donates an electron pair to our carbon, which pushes up the bonding pair of electrons to make a lone pair on the oxygen, and we get this species here, which is going to rearrange into carbonic acid, which more traditionally would be drawn like so. So if we have increased the amount of carbon dioxide in our waters by 35% and carbon dioxide reacts with water to make carbonic acid, well, that means we've also increased the amount of carbonic acid in our waters by a significant amount. We've talked about the pH scale previously. We know that neutral water has a pH of 7, and we know that pH is a logarithmic scale, meaning that every time we go down 1 pH unit, we are increasing the acidity of our solution by a factor of 10. And I think that this logarithmic scale is the main reason that ocean acidification hasn't got as much attention as it should, because it doesn't seem very dramatic to say, well, the pH of my body of water has decreased by 0.3. But the problem is that if the pH of your body of water decreases by 0.3, it actually means that it's 3 times as acidic as it used to be. And so we need to understand that about logarithmic scales. And those are the numbers that we're looking at. In pre-industrial times, the average ocean pH was 8.2. We've dropped it to 8.1. That might not seem like a big deal, but like I said, that is an increase of acidity of 35%. That really is a big deal. And if we keep going the way that we're going and don't do anything about the carbon dioxide levels, we're looking at the potential for an ocean pH of 7.8, or ocean water that is 3 times more acidic than it used to be by the year 2100. And why does this matter? Well, it matters because a lot of the organisms that live in the water, particularly those at the bottom of the food chain, have shells made of calcium carbonate. And those shells made of calcium carbonate stay in the solid state at a pH of 8.1 or 8.2 because that's a high enough pH that we have saturated our oceans with carbonate ions, and so the carbonate salts stay in the solid form, stay precipitated. But as the pH drops, as we increase the acidity, we also increase the solubility for those carbonate ions. Acid in the water can react with the carbonate to make bicarbonate, which dissolves. And so effectively, you could, first of all, dissolve existing carbonate structures, but second of all, prevent those organisms, those tiny little shellfish and such, from generating their own carbonate shells. And if you take out the bottom of the food web, there become very significant consequences for the species at the higher levels of the food web, which includes us when we eat fish, if there's nothing for them to eat. This image here shows you what happens when you take a tiny shellfish and you put it in pure water. So this is not acid, this is pure water. But because of the fact that there's no carbonate dissolved and we're dealing with a pH of 7-ish, then you can see that we start to introduce all sorts of little jaggedy, ripped away pieces. Of course, we didn't completely kill this poor little organism by leaving it in until it completely dissolved. Whereas you would have this nice, smooth, properly built shell in the calcium carbonated saturated water. And so at the end of the day, if we're going to pump carbon dioxide into our atmosphere and not do anything about it, not do anything to lower those levels, we do need to worry about the fact that the carbon dioxide is going to dissolve in our lakes and rivers and oceans. It is going to lower their pH. It is going to make them more acidic. And if that effect gets too significant, we're going to start preventing shellfish and other similar organisms at the bottom of the food chain from being able to survive. And if they're not around, then the species that eat them won't be around, and we're going to have really substantial consequences on the Earth's food web. And so it blows my mind that we're not talking about this. And I think the simple fact is it's not as media friendly as monsoons, and people really need to understand that that logarithmic scale is getting in the way of them understanding what a big deal this is. 0.3 pH difference